Okay, so I've copied out the term we want to prove. We've got our invariant P and our variant E here. And this is the statement we want to prove. So I've color-coded all the parts so you can see which part is the P and the B and the E and etc. So we want to prove this statement. And even though it's square braces, all our rules are actually completely identical. The only rule that changes is the while rule. So all of these rules here are exactly the same in total correctness land. So you could write these rules down with square braces and they'd all work. It's only these two rules that are different between partial and total correctness. So all our rules we're going to apply here are just going to be like these standard Hall logic rules. Okay? So let's just keep them safe here. Fold that over. There we go. Then we've got a nice little rules reference sheet here. We'll keep him over there because we'll need him. Alright, so how do I prove this? I've got two snippets of code. Looks like I'm going to have to do the sequencing rule, right? So I'm going to have the first condition, all of this junk, t equals I factorial, and I is less than or equal to n, and I is strictly less. You know what, the first thing I'm going to do is I'm going to do precondition equivalence and all that to clean this up a bit. So t is equal to I factorial, and I strictly less than n. I can drop this term out because it's redundant. And n take I is equal to m, and then I is equal to I plus 1. T is replaced with t times I, and then our post condition is nothing I can really delete there, so I guess I'll leave it the way it is. T is equal to I factorial, and I is less than or equal to n, and n take I strictly less than m. Okay? So if I can prove this, then I can prove that. So I just got rid of a redundant term. Okay, so now we'll do sequencing. So I'm going to have my precondition, t equals I factorial, and I is strictly less than n, and n take I is equal to m, and then the first bit of code, I is assigned to be I plus 1, and then mystery statement Q, second bit of code, t is assigned to be t times I, and our post condition, all of this rot. T equals I factorial, and I is less than or equal to n, and n take I strictly less than m. Okay? Yada yada yada, do assignment rule backwards, replace the t's with t times I. So you can see this proof's going to be pretty similar to this proof we did before. Just got these extra terms kicking around here we have to deal with. So assignment rule backwards, replace t with t times I equals I factorial, and I is less than or equal to n, and n take I strictly less than m. Copy our q over, t times I equals I factorial, and I is less than or equal to n, and n take I strictly less than m. Alright, this is true by assignment. How am I going to prove this statement? Looks like my old friend copy up the post condition and do assignment rule backwards is probably going to do it. So I'm trying to make this as algorithmic as possible for you. So t times I equals I factorial, and I less than or equal to n, and n take I strictly less than m. I is assigned to be I plus 1. So now we replace all the i's with I plus 1s. This is going to be quite lengthy. T times I plus 1 equals I plus 1 factorial, and I plus 1 is less than or equal to n, and n minus I plus 1 strictly less than n. So n minus I plus 1 strictly less than m. Okay? Can I do precondition strengthening to get from here to here? Well, I sure hope so. So if I assume this property, t equals I factorial, and I is strictly less than n, and n take I is equal to m, can I get to this property here? Well, if t, so let me just scribble in the margin again. If t is equal to I factorial, multiply both sides by I plus 1, ti plus 1 equals I plus 1 I factorial, and then you can move that in sides. Then we get I plus 1 factorial. So certainly this condition is true. So we get t times I plus 1 is equal to I plus 1 factorial. and we need this condition. So if I is strictly less than n, then I plus 1 is less than or equal to n. That's fine, that already works. Okay, and the last condition we require is that if n take I is equal to m, that needs to imply n take I plus 1. So n take I plus 1 is strictly less than m. Okay, so we need to prove this implication here, which shouldn't be too hard. So if n take I is equal to m, then that means n take I take 1 is strictly less than m, right? Because if this term here is equal to m, if I minus something from the left, it's strictly less than m. Then I can collect these terms together and subtract I plus 1 is less than m, which gets me the thing I wanted. Cool. So then we have n take I plus 1 is less than m. So this whole statement is true by math. So now my proof is done. Well, give me a moment. So 1, 2, 3, 4, 5, 6. So this is true by assignment. This is true by math. This is true by pre-con strengthening. Lines 1 and 2. Assignment. Sequencing 3 and 4. Precondition equivalence. If I'm being pedantic, I really should write this thing here as equivalent to this thing here, but it's forgivable to just write precondition equivalence of 5. And now, where's the rest of the proof go? So what I can do is I can then apply the while rule, this while rule here. So we'll stitch that part there, and then we'll keep going. So line 7 is I need, where are we? I need this condition to hold. P and B implies E is greater than 0. So P was T equals I factorial and I less than or equal to n. That's my P. And B was I strictly less than n. Does this condition imply E, which is n take I, is greater than or equal to 0? Is this true? Well, again, let's kind of just scribble in the margin and check that it works. So if I have I is strictly less than n, then that means n is strictly greater than I, which means n take I is strictly greater than 0, which means n take I is greater than or equal to 0. So yes, this is indeed true by logic. So then I can put this whole statement together with this whole statement using my new fancy while rule to get what I really wanted. So we will put this here. So I've got all of this junk. I've got P and B and E equals M. Do the code S. Then afterwards P still holds and E is now strictly smaller than what it was. I've got P and B implies E greater than 0. So then I can apply this new rule here to obtain P, T equals I factorial, and I less than n. While B, I less than n, do the magic code, increase I by 1, multiply T by I, and then my post condition, P and not B. So T equals I factorial, and I less than n, and it's false to say I is strictly less than n. Okay, by the while rule, total correctness, lines 6 and 7. And now the rest of the proof is identical to what was before, because this line here and this line here are totally identical apart from swapping braces for squiggle brackets. So what you can do is we can just sort of slip this underneath. There we go. Oh, you can't really see that. I'll fold it over. Lucky me that both lines happen to be line 8. Yeah. So then you can just sort of pretend these have got square braces instead of squiggle braces, and the proof to get this thing with square braces is completely identical to the proof it was before. So you just follow the proof we did before, but with square braces instead of squiggle braces, and then at the end, you finally get the statement that you wanted. You finally get this thing here, but you're guaranteed termination. Okay? So total correctness is not too much more difficult. Again, the tricky part is trying to find the variant, right? Oh, you can't see that. Let me just put that down. You have to find the variant. So you have to find an invariant P, which if you proved partial correctness, you would have done anyway. Then you have to find a variant E, and then once you've done that, it's the same proof as before, just with a little bit of extra legwork, okay? So that's how we do the while rule with total correctness.